Hello, in this video we'll be discussing waveforms, specifically ones that we might see displayed on a waveform generator or oscilloscope. So what exactly is a waveform? Well, in the broadest definition, it's just a graph showing change over time. It could be electrical signals, sound waves, etc. On this case, we'll be focusing on it showing change over time in electrical signals. Now, starting with standard DC voltage, it's nominally just a straight line on an ideal circuit at whatever given voltage. So in a circuit simulator, it'll pretty much be a straight line. In real life, you're going to get noise, interference, the probes on whatever you're using, oscilloscope may have some issue, there may be shakes, so you're going to see some of that in the display of DC voltage, which is normal. AC voltage, on the other hand, is a sine wave that goes back and forth at a specific frequency between positive and negative voltages, often 50 or 60 hertz. You can also get other things that are sine waves that aren't technically AC voltage. Circuits can transfer one waveform or a lack of one to a different waveform. The most common waveforms, and again, this list can be argued on which are primary waveforms, but I'm going with square, sawtooth, pulse, triangle, and sine wave. Rectangular waveforms are really just a form of square wave. Trigger waveforms are just a very narrow pulse wave. Sound travels in waves, so waveforms, as I said, could also display the characteristics of an audio signal, which becomes an electrical signal. You might also see it as multiple waveforms merged together at different frequencies. Waveforms can also be irregular and custom, but still defined by a function. Waveforms have characteristics, starting with the wavelength, which is the length between two peaks, max or peak to peak. It also might be called, or two troughs or valleys, minimum, and indicated by the symbol lambda, which is equal to wave speed divided by wave frequency. Then you've got amplitude, which for our purposes is how high or low the voltage goes in the wave, and it's indicated by an A, and the range depends on if the wave is unidirectional or bidirectional. Velocity, also known as wave speed, indicated by V, which is equal to wavelength times period or wavelength times frequency, and is usually measured in seconds, milliseconds, microseconds, but could be as fast as nanoseconds. Period is the time it takes for two peaks or valleys, or the time between two peaks or valleys, and is wavelength divided by velocity and indicated by t. Frequency is the number of periods per second, and it's 1 divided by period or time. Again, you also have unidirectional or bidirectional, and the characteristics of the medium the wave travels through can be important. For electrical signals, not a big characteristic, but when we start talking about sound waves and audio, it will be. First, we'll talk about a square wave because you'll encounter this when reading digital signals. It's characterized as a positive waveform where each peak and valley are the same width and are completely uniform, or at least in an ideal circuit. Even if it's not uniform and it's square-like, then we'll still call it a square wave. The ideal version of a digital signal with the peaks being ones, the valleys being zeros, or you could have the reverse. It really depends on what's interpreting them. Conversion from analog to digital usually leaves something square-like. We also have the concept of rising and falling edges. When we talked about oscilloscopes, we mentioned triggering on an edge. Next, we have the sawtooth wave. It's characterized as a steady rise and then a sharp, steep decline. It can be a slow positive ramp and a steep decay, or it could be a vertical rise and a slow negative ramp, in which case we'll probably call it a reverse saw wave. It's kind of similar to the behavior that you might see with a capacitor if the discharge is instant and it's not going back through a resistor, but its shape really depends on a number of factors. Next, we'll talk about a pulse wave. It's a form of square wave, technically. It's a fairly short width at each peak, followed by a much larger valley, usually 5 or more times. Often the waveform you see for clock pulses, turning something on or off, timers, etc., since you really only need a brief signal each time. Then we have the triangle wave that's characterized by steady equal slopes on both sides, and it's often bidirectional, inverting every other half period. You often see this with relaxation oscillators. Internals to a function generator will often start with a triangle wave and then convert it to other things. You also see it with an integrator that's driven by a square wave. The key here is it rises steadily. It's at a point very briefly, and then it goes right back down, and the two slopes are basically even. And then we have the sine wave. It's usually characterized by being bidirectional with rounded peaks and valleys of equal size. This is what you're going to see with alternating current, but there'll be sine-like wave or sinusoidal, I can never say that word, waves that may just be positive or negative. And anything that's kind of close to that, we still sort of call a sine wave. Now, in a previous video, I've gone over oscilloscopes, but just to remind you, it's an electronic test instrument that graphically displays change over time, usually voltage, current, or whatever. Older oscilloscopes effectively used a cathode ray tube to trace the various waveforms on a screen. With analog versions, the analog signal would directly drive the electron beam. Some models even just use matrices of light bulbs to roughly show a pattern. They used to be really expensive. The first successful models were like $10,000 in today's dollars. Not something the average hobbyist could afford, but it was still in the wheelhouse for somebody who could afford to basically put the to buy a car. Varying prices, cheapest models can be, 30 bucks. Probably want something a little better because they have limitations. But they'll allow you to see waveforms, assuming your signal actually provides one. I should also mention functions or signal generators. These are devices that can output specific waveforms, usually at specific frequencies or even specific voltages. Gives the user the ability to generate a specific waveform without the need to build a circuit to do it. Cheap ones can run you like 30 or 40 bucks, but you get what you pay for. More expensive models are going to have more frequency ranges, more features, and generally better. A number of circuits can output several different waveforms, although sine wave generation can be difficult, the most difficult in my experience. Square wave generation tends to be the easiest to output. Just have something that outputs a Schmidt trigger. They'll also call it function generator because sometimes you can just put in a function to generate the waveform. All right, here are in every circuit, and I have 5 different waveforms, and you can see how the light looks. I believe we started with the square wave right here, which I've actually set the source to go, so it has a period of 3 milliseconds with the 50%. That's a bit of a decay value, but I'm going to ignore that for the moment. So let's see what that looks like. So, yep, pretty much all equal squares, the valleys and the peaks, very uniform, going between 0 and 5. And that's the kind of blink pattern you've got right here. So let's look at triangle wave right here. It's only reached its peak very briefly before coming immediately down, and both slopes are actually even. Then let's see, sawtooth is this one right here. Slowly gets brighter and then it suddenly drops off. I don't have an example of a reverse sawtooth, though it wouldn't be hard to make one. And then over here we have a pulse. Whoops. All right, there we go. See, there's a lot of space between each because you only need the pulse for so long. Um, and if you're trying to build something, usually there's data sheets to give you an idea of what the pulse should be. The trigger would just be a even thinner pulse. And then we've got our sine wave over here. It's going between 5 and -5. It looks a little, it is a little, well, let's bring it out so it looks a bit more wavy, but yeah, everything is just uniform. And we also have some other options. We can actually adjust like the amplitude, frequency, phase, and then there's really only three waveforms, but again, you can adjust them for whatever you need. All right, let's move over to Falstead here, and I've got basically the same idea, although we can actually define these waveforms with the voltage source a little better. We've got a sine wave at the top here, the red light. We've got a square wave next, the, was that green or yellow? We've got a triangle wave with the blue. We've got a sawtooth, which I think the square wave was green, and the sawtooth is yellow. And then we've got a violet or purple for the pulse wave. And I mean, again, we can adjust these to fit whatever we need. We've got DCAC, square wave, triangle, sawtooth, pulse, and even noise. And we can define some of the specifics here, frequencies, duty cycle, etc. Here's another example in SIMUIDE. I've done a square wave and then I've done a pulse. Um, and this is a sawtooth. This is a sine wave. This is random noise. And then this is a triangle at the bottom. And you've got both the clock and you've got fixed voltage and wave generator.